2003 Canadian Open Mathematics Challenge, Part B. In the diagram shown, whole numbers are to be placed in the 10 circles so that the sum of the numbers in the circles along any of the 10 straight lines is 15. For example, A plus G plus K is 15 and E plus I is 15. If K is 2 and E is 5, fill in the whole numbers that go in all of the circles in the diagram. They've given us K is 2 and E is 5. So here we go. Any straight line must add up to 15. So we just kind of go with that rule. Let's go with this one first. E plus I is 15, right? So that means I must be 10. So you see how this is going to go here? This straight line right here, that all adds up to 15. So 2 plus 10 plus C is 15. So that means C must be 3. Where do I go next? This one, those three have to add up to 15. 5 plus D plus 3 is 15. So D must be 7. This is a straight line. So 7 plus B is 15. So that means B must be 8. And you just kind of keep going like this. Where do I go next? I think this one. A plus 8 plus 3 is 15. So that means that A must be 4. And this straight line adds up to 15. So 4 plus G plus 2 is 15. So that means G is 9. This straight line adds up to 15. So G, which is 9, plus H plus 5 is 15. So that means H is 1. And then I think there's only one left, this one. So that means 1 plus F plus 8 is 15. So therefore F is 6. And I think that's it, right? I've labeled all the letters. Yes, I have. So that's basically what they wanted to do to part A. Part B. Suppose that K is 2 and the value of E is unknown. Find a formula for each of B and C in terms of E. A clearly labeled diagram is sufficient explanation. Well, they've told us that K is 2 and the value of E is unknown. All right, so we want formulas for B and C in terms of E. Okay, that shouldn't be too hard. From this straight line, we can conclude that 2 plus E plus B is 15. Okay, so that means that B is equal to 13 minus E. So I got 1. They wanted B and C in terms of E. Okay, so I'm halfway there. And then where else can I go now? This line right here will give me another equation that 2 plus I plus C is 15. So that means that I is equal to 13 minus C. Yeah, okay. I'm going to need a little bit more help here, so I'm going to use these guys right here. That one, those two. Those two basically tell me that E plus I is 15, and therefore I is equal to 15 minus E. Okay, great. So I is equal to 13 minus C is equal to 15 minus E. I can set them equal to each other. So that means 13 minus C is equal to 15 minus E, and therefore C is equal to E minus 2. And that's it. That's what they wanted. They wanted B in terms of E and C in terms of E. So that takes care of that one. Let's move on to part 2. Show that E must be equal to 5. All right. So where do I want to look here? B, D. Let's look at this line right here. That one. That line tells me that B plus D is equal to 15. So that means that D must be equal to 15 minus B. Well, we have already figured out that B is equal to 13 minus E, so let's substitute that in. Minus 13 plus E, right? It would be minus minus. So that means this is 2 plus E. D. And then we can look at this line. From that line, we can conclude that, running out of space here, that E plus D plus C is 15. Well, I think we have everything in terms of E. I think that's why they wanted us to do part 1. So that would help us in part 2. E plus D, well, D we just got was 2 plus E. And then C we have over here is E minus 2, and that's all equal to 15. So this looks like 3E is 15, and therefore E is equal to 5. And that's what they wanted you to show in part 2. Now we get to part C. Suppose now that K equals X, where X is unknown, prove that E must still be equal to 5. Okay, so K is now X. All right. Well, to explain this properly, or to explain this in an easy way, I will sort of backtrack and just show you exactly what I did before, but this time with not K equal to 2, but K equal to X. And it'll show you that it basically is the same strategy. Okay, so if K is equal to X, then that means our equations change a little bit, right? Instead of this 2 plus E plus B, it actually becomes X plus E plus B is 15 for that line right there. Okay, then that means that our equation now for B is actually B is equal to 15 minus X minus E. Same thing over here. This equation we previously did for K equals 2 for that line, but now K is X. So instead of 2, we have to put an X. So X plus I plus C is 15. So that means I is equal to 15 minus X minus C. Okay, continuing in the exact same way, where did we go next? We went here, right? So that was E plus I. Where's E and I? Okay, E plus I is 15. That doesn't change. That's exactly the same. So I'll just keep it. I'll just keep that. This part we'll just keep the way it is. But now we equated these guys, right? We equated that I equals I. So we have to equate that. We have 15 minus E from here. But over here, it's slightly different, right? This is a little bit different. So I this time is 15 minus X minus C, like that. So the 15s disappear, and then if you put C on one side, you get E minus X. Okay, great. And then we continue in the exact same way yet again. Let's see here. That we look at these two, B plus D. That doesn't change. B plus D is still 15. So B plus D is still 15. Like that. And B is right up here. So we've got 15 minus X minus E plus D is 15. If you make that substitution. 15s disappear, so therefore D is equal to X plus E. Okay. Now we have one final, let's see which line, this one, E, D, and C. If we use that, E, D, and C, E plus D plus C is 15. Let's make our substitutions. E, we just leave it alone. D is here, X plus E. C is here, E minus X is 15. Looks like the X's cancel, 3E is 15, and E again is 5. So we have shown that E is still equal to 5 when K is equal to X. A barn has a foundation in the shape of a trapezoid with 3 sides of length 6 meters and 1 side of length 12 as shown. Determine each of the interior angles of the trapezoid. Well, I'll just keep it simple. Just drop a perpendicular like that. Another one here. These are right angles, therefore. And from here to here is 6. And this whole thing is 12. So that means this and that must be 3 each because of the symmetry of this diagram. And then easily with Pythagoras, you can figure out if this is x, for example, this distance. 3 squared plus x squared is 6 squared. And if you do that math, you will be able to figure out that x is equal to 3 root 3. So this is 3 root 3. So when you look at that triangle, the sides are in the ratio 2, 1, and root 3. And any triangle, any right triangle, well, I mean, we know it's right because of the way I drew it, but bottom line, what I'm trying to say is that any triangle that has the ratio of sides of 2, 1, and root 3 is a 30, 60, 90 triangle. 30, 60, 90 triangle. Where this is 30 degrees, this guy, and this angle is 60 degrees. So that helps us figure out the interior angles. The interior angles, well, this is 60, that's 60, like that. And then since this is 90, this whole thing is 90 plus 30, so that's 120. And that's also 120. So I guess I can draw it here like that. This is 120, this is 120, this is 60, and this is 60. So those are the interior angles of the trapezoid. Chuck the llama is attached by a chain to a point on the outside wall of the barn. Chuck is smarter than the average llama and so realizes that he can always reach the area between the barn and where the chain is fully extended. If Chuck is attached to point A with a chain of length 8, what is the area outside the barn that Chuck can reach? Well, we've got to draw this and I've got to explain it. So here we go. This diagram is really just for explanation purposes. It doesn't have to be a work of art. I'm just trying to explain to you how this chain will look like, will behave. So there is a chain attached to this point, and it is 8 meters, according to what they say. So it can stretch out like that, right? And it can form a circle, well, part of a circle at least. So, like I said, it'll be able, this won't be a beautifully drawn diagram, but you kind of get the point that it will be able to kind of go around like that in a circular format with a radius of 8 until it stretches out to here, and then it won't be able to go anymore. So I hope you kind of get the idea of what I was trying to show you. Now, once it gets to the edges like that, this is a barrier or fence or foundation, whatever. So it can't go, but it can continue to go with just that segment of the chain. Similarly here, I might have drawn this a little bit too big, so I'll have to like that. So I'll just edit it a bit. So something like that. I mean, it's not a work of art, but you guys understand. So let's talk about this now. Now, this part right here is part of a circle. And these are also, this one and this one are also parts of a circle. Now, how much though? How much is the area? Well, the area depends entirely on the degrees. So we have to figure out the degrees of this, and this segments. Okay, that shouldn't be that hard. That's why they wanted us to figure out the interior angles. We already figured out from the previous part that this is 60 degrees. And therefore, this angle in here will be 120. Okay, because this is a straight line. Well, at least it should be a straight line. And then we figured out that this was 120 in the previous part. So therefore, this angle in here is 60. Okay. And then we also knew that that's 120. So if we were to extend that, as a straight line, this whole thing is 180, right? And then this, therefore, would be 60. So there we go. We know the interior angles of those segments, so we can now figure out the area. The first part, which is this big guy right here, that is going to be pi r squared, but not the full pi r, only 240 degrees of it, because this was 180 and that's 60, so that's 240 in total. And of course we have to divide by 360 because 360 represents the full rotation all the way around of a circle. Okay, that takes care of that part. Then this little guy in here, that's also pi, but it's a different r. So we'll call this big R. So this is small r squared, and it's 120. So 120 over 360. And then this small area is also pi r squared, but this time 60 over 360. And I think that should be it. That should be enough to calculate this. Okay, so let's work with this. Pi r, what's big R? Big R is this full radius, which is 8. That's the full length of the chain. So 8 squared, and this is 2 over 3, correct? Yeah, 2 over 3 if I reduce it to lowest terms. Now, this little r, the little r is from there to there. So this is 6, right, according to the question. So that little radius would therefore be 2. 8 minus 6. Okay, so pi 2 squared, and this is 1/3. And then finally the last one, that's also going to be a radius of 2, since this top was 6. So that's going to be pi 2 squared, and then that is 1 over 6. And that should be correct. So 64 times 2 divided by 3, 128 over 3 pi. This is 4 pi over 3, and this is 4 pi over 6. And if you get a common denominator, that's actually 2 pi over 3. And when you reduce it, so that should be 128 plus 4 plus 2 is 134. 134 pi over 3 is the correct answer. So that takes care of this guy. Okay, same story, I think, for the last part. If Chuck is attached to some point P along the wall AB with a chain length of 15 to determine the location P, which restricts Chuck to a minimum area. Okay, actually it's not identical. It's a little bit different. But the fact that we did the previous part will really help, I think. It will make this part seem not as bad, not as difficult. If they jumped directly to this, it might seem a bit daunting. But since we already got comfortable with the previous question, this shouldn't be so bad. So let's label this as carefully as we can to make this have some level of sense. A is here as before, B is here as before. But now they've given us this P. Now I don't know where P is, so I'm just going to put it there. And extending out from P is a 15-meter chain. And it's going to go all the way around. So it'll be able to go all the way around until it gets to about here, right? So that'll be a full I guess, segment of a circle. And similarly, it will go all the way around until it gets to there, and that will also be a full segment of a circle. But then it will have to sort of behave in a different way when it gets to here. It will stretch the full length that it can, but it'll be a little bit shorter because now you can only stretch this guy because this part is covered by the boundary. So it'll come down, but it'll be shorter. And then similarly, this part, I'll just exaggerate it a little bit, like that. This part, again, will be able to stretch down here, but then there will be a little part left over, and that part will be able to stretch like that. So you've got a little bit, and then like this. And same thing here, this will have to be able to make a smaller kind of segment. So hopefully that makes sense. Now let's label this carefully. Labeling part is crucial and we don't make any mistakes. From here to here is 6. That's according to the diagram. But from here to here, we don't know. So I'll have to call that distance x from A to P. Similarly, from P to B, we will have to call 6 minus x, since the full distance is 6 and this was x. Okay. This from here to here, that's a full 15, so we can put that there. But from here to here, that's not a full 15. It's 15 minus 6 minus x, right? This whole thing is 15, but then this is 6 minus x. So I've got to put 15 minus 6 minus x. And that is 9 plus x, if you do that math. So this is 9 plus x from B till the edge there. And therefore, this would also be 9 plus x. This distance right here. Okay. Now let's keep going. We have to figure out this segment right here. This segment. Well, that's straightforward. It's going to be 15 minus x. And then there, that 15 minus x is also the same as that. So that's 15 minus x. Okay. Then it changes, right? This is no longer 15 minus x. That segment is going to be 15 minus x minus that. And that is, according to the question, 6, I believe. So you've got to take this 15 minus x and subtract from it 6. And when you do, you get 9 minus x. So 9 minus x is this distance right here. 9 minus x. And that's also the distance that it travels from there to there. So I'll put that in there, 9 minus x. And then finally, you've got to chop off this distance, which is 6, from the 9 minus x. So 9 minus x minus 6, and that becomes 3 minus x. And that's this distance right here. So I'll just put that in there. That is 3 minus x, and so is that distance, 3 minus x. Okay, so hopefully that wasn't so bad. Now the full area is going to be very similar to before, fractions of circles, right? But we got to figure out all the angles first. Okay, well, we figured out in part, what was it, very first part of this question, some of those angles. If I remember, this was 120. This was 60, and that's also 120 and 60, right? So that means that this angle in here will be 120. So just put that in there, 120, the angle. Therefore, this angle in here will be 60. This whole thing is 180, right? That's just a straight line from here to here that I drew. So that's going to be 180. And then what else do we need here? We need this guy. Well, that's 60. That's pretty straightforward. That's 60. And this angle in here is 120. Since this angle was 60, this is 120. Okay, I think that's enough. All right, let's go and figure this out. So where do we want to begin here? First thing we want to do is, I guess the only one that involves the 15 is this whole thing right here. This one. So that's the first one. So that would be, that's 180 degrees, right? So 180 over 360, and then pi r squared, r is 15. Okay, that takes care of that guy. So that takes care of this segment. And then next one, we can do, I guess this one, that would be 60 over 360, and then the radius in that I have labeled as 15 minus x, so pi 15 minus x squared. Okay, next one is, it doesn't matter which order you do it in, but I guess we can do this one. That segment would be 60 is the degree, and then pi r was 9 minus x here. And then let's see what else. This little guy here, that's going to be 120 over 360, and the radius there was 3 minus x. And then finally, don't forget about that one. That's going to be 120 over 360 in terms of its degrees, and the radius was 9 plus x. Okay, now we have to crunch out these numbers, and we're going to get a quadratic, and then we can do what they're saying, which is minimize the area. Okay, so here we go. Okay, let's crunch out these. So we're going to have 1/2 225 pi plus 1 over 6 pi times 15 minus x squared plus 1 over 6 times pi 9 minus x squared plus 1/3 pi 9 plus x squared, and finally 1/3 pi 3 minus x squared. I think I jumped over one, but it's all the same. Okay, let's keep going. Now we got to expand all this. So we got 225 pi over 2. And I'm going to factor out a pi over 6. That's going to make things easier. And if I do, I'll be able to 15 minus x squared plus 9 minus x squared plus 2 3 minus x squared plus 2 9 plus x squared. Okay. Yeah, that is how this is going to proceed. Okay, good. So now let's do all the numbers here. We got to expand and all that stuff. So this is going to be pi over 6. And when we expand this, 225 minus 30x plus x squared plus 81 minus 18x plus x squared plus, now I've got to multiply by 2, so don't forget to do that. And when you do, it'll be, let's see here, 18 minus 12x plus 2x squared. And the final one, this guy, will be 162 plus 36x plus 2x squared. Okay, not so bad. 225 pi over 2 plus pi over 6. Now we got to add all these like terms up, and when I do, I'm going to get 1 2 3 4 5 6 x squared, and then it'll be, let's see here, minus 24x, and then 225 81 80 486. Okay, so that's not so bad, right? Okay, good news is these 6's cancel. So we got an x squared minus 4x plus 81. All right, good. And then we'll put this 225 pi over 2 out here. Okay, perfect. Now we can get to the final, well, sort of final step, which is completing the square. You have to complete the square in order to get that minimum value. So basically, this is a parabola, right? So I'll just draw a little sketch of a parabola here to let you guys sort of understand what's happening. You've got a parabola, and I don't know what it looks like, but let's just say it looks something like that. And this is x, and this is your area. So at some value of x, this area will be at its minimum. And that's the value of x that we want to figure out. How do you do that? By completing the square. So you complete the square, you take this coefficient, in our case it's -4, then you take half of it, which is -2, and then you square it, which is +4. So it would be like this, pi x squared minus 4x, and then you would put that +4 in there, and then immediately you have to subtract it, and then you continue with the rest of it exactly the way it was. Now the whole point of doing that is it allows you to factor, and in particular those terms factor out very nicely when you do that. And then don't forget to kick that out of the bracket. So 81 minus 4 is 77, and then when you kick it out of the bracket, do not forget to multiply by that pi. So it'll come out as 77 pi. And this is 225 pi over 2. Yeah. So that means this is pi x minus 2 all squared, and then when you add this, you get 379 pi over 2. So that means that when x is equal to 2, this whole thing vanishes, and you're left with an area of 379 pi over 2. So going back to our diagram, it basically means when this is 2, when x is 2, the minimum area is achieved, which in our case was 379 pi over 2. And I think that's what they're asking for. They just want you to figure out the value of x. So that's the answer. In the diagram, the two circles C1 and C2 have a common chord AB. Point P is chosen on C1 so that it is outside C2. Lines PA and PB are extended to cut C2 at x and y respectively. If AB is 6, PA is 5, PB is 7, AX is 16, determine the length of XY. Let's label this. We've got AB is 6, so this guy in here is 6, I guess. And then PA is 5, and PB is 7. Okay. AX is 16. And what do they want? XY. So they want that, I guess. Okay. All right, where do we start here? Well, I think we're going to have to label a few things here. The first thing I will label is I'm going to need an angle. So this angle right in here, that angle right in there. So angle PAB, that I will call theta. So I'll just put theta in there. And therefore angle XAB will be 180 minus theta, right? Because that's a straight line. So, okay. Now notice something that XYBA, this quadrilateral XYBA, its vertices are on a circle. So XYBA is therefore a cyclic quadrilateral. And the reason is because it's inside a circle. It sits on a circle, basically. Its vertices are on a circle, and any such quadrilateral is called cyclic. So why is that important? Because in a cyclic quadrilateral, the opposite angles add up to 180. So that angle and that angle would add up to 180. That angle and that angle would add up to 180. So what that means is that angle XAB plus angle XYB would add up to 180. Now XAB I've just called 180 minus theta, and XYB angle Therefore, we can isolate angle XYB would be just theta. So XYB, this angle, would be theta. So that helps us a lot because now we have a similar triangle situation. We have similar triangles as follows. Triangle PAB is similar to triangle PYX. Now, I'm going to prove it by drawing both of them. Sometimes it's not as clear, so I'm going to draw them both. Let's draw angle PAB. So PAB is like this. Here's P, here's A, here's B. And the angles, well, this one I had already labeled, right, as theta. And this angle, whatever you want to call it, I'll just call it alpha. And then this angle we'll call beta or gamma. Yeah, whatever, doesn't matter. Now let's draw the other guy, PYX, this triangle. PYX. PYX is essentially the big one all the way. So PXY like that. And if you notice, this angle is the same. Alpha, it's common to both triangles. But then this angle is theta, according to what we had figured out. So if two angles are the same, the third angle must be the same. So this is beta. So as you can see, that's why they're similar, because they have the same angles. And then based on that, we can create a relationship between the sides. XY over AB is the same as PX over PB. And therefore, XY is equal to PX times PB times AB. And PX is what? That one we know. P to X is all the way across, so that's 21. PB is 7. And then AB is here, 6. Okay, so we got 3 times 6, 18. So that answers part A. Two circles C3 and C4 have a common chord GH. Point Q is chosen on C3 so that it is outside C4. Lines QG and QH are extended to cut C4 at V and W, respectively, so that no matter where Q is chosen, the length of VW is constant. Show that. Okay, so it's the same diagram, I believe. The only difference is they've changed the letters. Yeah, it's the exact same diagram. So instead of this being C4, it's C4 this time, and this is C3, which doesn't really matter. This is now Q. So put in a Q here. And then this is now G. And this is H. And this is V and W. And I think that's it. I think those are the letters. So it's the exact same diagram. And they just changed the letters on you, which, you know, whoop-de-doo, right? Who cares? Okay, so what do they want us to prove? They want us to prove that VW, this distance, VW, is constant. Okay. Let's see if we can do that. Well, we will let VW equal K, since we have to show that it's a constant. And then we'll join V to H. So V to H, we'll join that like that. Join V to H. And then we will join W to G. So W to G like that. And those are straight lines, or at least they should be straight lines. There. I don't know if that's any better, but okay, now there's a rule that angles that subtend by the same 2 points are the same. So for example, I'll explain. You've got this point V and this point G. If you extend them both, you get this angle. But you can do that again in another direction. You can go this way, that angle. Those two angles would therefore be the same. They're subtended by the same lines. So that means that angle VGW is the same as angle VHW, as I have already shown. Now, in the circle C3, we have an angle CQH, or GQH, I should say. So this is G, this is Q, this is H. So it's this angle in here. And that angle I will call alpha. So let's label that in there. This is alpha right there. And then in circle C4, we have an angle GVH. So that's this one, GVH. That angle we will call beta. So GVH, I will call beta. So put that in there, beta, like that. And according to this rule, that means that the angle GWH is also beta, correct? Because they are both subtended by the same 2 points. We have GVH, which is there, subtended by G and H. And then we have GWH, which is also created by extending those 2 points, G and H. So therefore, GWH is also beta at that angle. Okay. Now we are down to our final stage of the question. A lot of setup in this question. You have to set up all these things in order to prove. Now finally look at, therefore, angle VHQ. This one, VHQ. And we're going to look at it from the perspective of that triangle. Angle VHQ from the perspective of that triangle is 180 minus the other two angles, which are alpha and beta. Correct? So that means that we can write this as angle VHQ is equal to our relationship with this angle, VHW. There's VHW, there's VHQ. Both those angles add up to 180, right? So VHQ plus angle VHW add up to 180. So angle VHW is essentially 180 minus angle VHQ. Well, VHQ, we can substitute that. So it's minus 180 plus alpha plus beta. And therefore angle VHW is alpha plus beta, like that. Okay, pretty good. And then we do the exact same thing for angle QGW. QGW is right here. QGW right there. And then from the perspective of that triangle, we can write it as that angle QGW is equal to 180 minus the other two angles, which are alpha and beta. And therefore, QGW and VGW, which is this, QGW and VGW add up to 180. So therefore, QGW plus angle VGW are equal to 180. Now that basically means that angle VGW is 180 minus angle QGW. Well, angle QGW, we have a formula right there, so substitute that in. 180 minus 180 plus alpha plus beta, and therefore angle VGW is equal to alpha plus beta. So now we've got two relationships. VGW and VHW are alpha plus beta. So VHW is here. VHW, this angle, we're saying is alpha plus beta. And then we're also saying that VGW, this angle, is also alpha plus beta. And if they're both the same, then that means V, which is this point, and W, which is this point, are fixed. And therefore, this is constant. So that's our final conclusion, that since those two angles are the same, you can write it out according to that rule. V and W are fixed, and therefore VW is constant in terms of its length. And that completes part B. The polynomial equation x to the power of 3 minus 6x squared plus 5x minus 1 equals 0 has three real roots, a, b, and c. Determine the value of a to the power of 5 plus b to the power of 5 plus c to the power of 5. If this is true, that means that x to the power of 3 minus 6x squared plus 5x minus 1 can be written as x minus a, x minus b, and x minus c, since those are the roots. Now, this question, we will need to use Vieta's formula, and in particular, its rules. If you have a polynomial of the form, let's say, ax squared plus bx plus c, then there's a formula for the sum of the roots, product of the roots. But in our case, we actually don't have ax squared. We have ax to the power of 3 plus bx to the power of 2 plus cx plus d. We have that kind of a situation, equals 0. So what is the formula? The formula states that the sum of the roots are equal to minus b over a. We're looking at this now. Don't get confused. Then the product of the roots of this polynomial is equal to minus d over a. And then the sum of products is c over a. Now the sum of the roots in our scenario up there, since the roots are a, b, and c, for us it would be a plus b plus c. Now using this formula applied to an equation of that form, it'd be minus b over a. In our case, there's our b, and our a is really just 1, right? So minus b over a in our case would be equal to 6. It would be minus 6 over 1. Product of the roots. Product of the roots, of course, is a times b times c. And if we apply minus d over a for an equation of that form to our equation, our d is minus 1 and our a is 1. So it would be minus 1 over 1, which is just 1. Sum of products. First of all, what does that mean, sum of products? It means AB plus BC plus AC. And that's C over A. In our case, our C is 5, our A is 1. So C over A is just 5. So these three formulas are very crucial to this question. So here we go. Let's begin. The first thing, of course, is that if a, b, and c are roots, they will fit into this equation. So that means a to the power 3 minus 6a squared plus 5a minus 1 is equal to 0. And similarly, b to the power 3 minus 6b squared plus 5b minus 1 is equal to 0. And the same story holds true for c, since they're roots. Now, what we're going to do is isolate in each of these for the power of 3. So in this case, a to the power 3 will be 6a squared minus 5a plus 1. And in a very similar way, b to the power 3 will be 6b squared minus 5b plus 1. C to the power 3 is 6c squared minus 5c plus 1. Okay. And if you take these three, and if you add them, on this side, you get a to the power 3 plus b to the power of 3 plus c to the power of 3 is equal to 6a squared plus 6b squared plus 6c squared. And then we get minus 5a squared minus 5, actually not squared, just a, minus 5b minus 5c, and then there's a plus 3 at the end. All right, great. Let's move along. And we're going to use all these guys, so I'm going to keep them, these results here. We're going to use them. So I will ensure that we keep them on the same screen. Okay, a to the power of 3, b to the power of 3, c to the power of 3. Factor out the 6, and we get a squared plus b squared plus c squared. And then we factor out the 5, and we get a plus b plus c, and then plus 3. Okay. Now, a squared plus b squared plus c squared, that we have to do a little bit of manipulation to get, which we will. So I'll just leave that. But a plus b plus c, that we already got. So that's really good. We can put that 6 in there. Now let's concentrate on this. I'll do it on the side here. You take just a plus b plus c, and then you square it. And when you do, you get a squared plus b squared plus c squared plus 2ab plus 2bc plus 2ac. This is indeed the correct expansion, collecting like terms. Well, a plus b plus c is 6, so that would be 6 squared on that side. A squared plus b squared plus c squared, well, I don't know. That's what we're trying to figure out. This part, however, becomes 2 times ab plus bc plus ac, and that we know is 5. So that becomes 2 times 5. So therefore, a squared plus b squared plus c squared is going to be this 36 minus 10, which is 26. So we put that in here. And then when you crunch out these numbers, you get 129 is equal to a to the power 3 plus b to the power 3 plus c to the power 3. So as you can see, it works out very nicely. But we have to figure out a to the power of 5 plus b to the power of 5 plus c to the power of 5. We're not yet done. Okay, no problem. The good news is that you proceed in the sort of the same way that you just did. Again, what you do is you take what you already did and just do it again. So, these guys up here, remember? In particular, this one, and this one, you multiply by a, b, and c. So multiply this by a, multiply this by b, multiply this by c, all the way through. That way you'll get a power of 4. So you will basically get a to the power of 4 is equal to 6a to the power of 3 minus 5a squared plus a. Right? You guys see what's happening here? So this will be b to the power of 4 is 6b to the power of 3 minus 5b squared plus b. And this one, when you multiply through by c, you get c to the power of 4 is equal to c to the power of 3, 6c to the power of 3 minus 5c squared plus c. So that's all it is. And then what you do is very similar to before. You add these together. And I will do that down here. So let's add them all. When you do, you get a to the power of 4 plus b to the power of 4 plus c to the power of 4 is equal to 6a to the power of 3, b to the power of 3, c to the power of 3 plus, minus, I should say, minus 5a squared plus b squared plus c squared plus a plus b plus c. So all I did to get this whole thing was I took these guys and I just added them all. So let's see if I can fit it on the same screen. Yeah, I can. So that's all I did. Took those three, added them together. Okay, now you'll see that it kind of all starts to fit in. This guy is 129 minus 5. This is 26. And this, well, that's 6. So there you go. And then when you crunch out these numbers, you get 650. Okay, we're very close. We just have to do the power of 5s now. To get the power of 5s, you do the exact same thing. You take these guys and you multiply through by a, b, and c respectively. So let's do that. You multiply through by a, b, and c respectively. So this becomes a to the power of 5, 6a to the power of 4 minus 5a to the power of 3 plus a to the power of 2, right? Same thing, this is b to the power of 5 is equal to 6b to the power of 4 minus 5b to the power of 3 plus b squared. And then this one would be c to the power of 5 is equal to 6c to the power of 4 minus 5c to the power of 3 plus c squared. And as before, you add them. So this plus that plus that. You see how this is all working out? And I think I can keep it on the same page. Yeah, I can. All right, so add those three, and you'll get a to the power of 5 plus b to the power of 5 plus c to the power of 5. And when you group them to like terms, it'll be 6a to the power of 4 plus b to the power of 4 plus c to the power of 4 minus 5a to the power of 3 plus b to the power of 3 plus c to the power of 3 plus a squared plus b squared plus c squared. All right. Well, this part we got recently, 650 is the answer to that. And so that is 6 times 650 minus 5 times this is, I think I got it somewhere, 129. And then plus a squared plus b squared plus c squared, it was here, it was 26. And then when you crunch out these numbers, you get 3281. And that is what a to the power of 5 plus b to the power of 5 plus c to the power of 5 is equal to. For b, if a is less than b is less than c, show that c to the power of 2004 is closer to its nearest integer than c to the power of 2003 is to its nearest integer. What they basically are talking about in this question is that, let's say, c to the power 2004 is equal to something, right? Let's say 7.2. It's 0.2 away from its closest integer, correct? Now, let's say c to the power of 2003 is 6 to the power of 3. Well, it's 0.3 away from its closest integer. They want you to show this, that c to the power of 2004 is indeed closer to its nearest integer than c to the power of 2003 is to its nearest integer. So that's sort of just some numbers to kind of illustrate what they want. Okay, well, so how do you do this? Well, it involves 3 steps, and I'll go through each of these 3 steps. So the first is we have to estimate the approximate values of A, B, and C. And remember, A, B, and C are the roots of this equation, right? Because this is a continuation of the previous part. So the previous part told us that f at x is equal to x to the power of 3 minus 6x squared plus 5x minus 1. Okay, so we have to figure out, is x equal to less than 0, 0, greater than 0? Well, if x is equal to 0, then obviously we can't have a situation where f at x is 0, because if x is 0, f at x would be equal to negative 1. So x cannot be 0. How about if x is less than 0? If x is less than 0, then we have a situation where this will be less than 0, this will be less than 0, this will be less than 0, and this is already less than 0. So that means if f at x is trying to be equal to 0, that would be possible, because under this scenario, f at x is also going to be less than 0. So that means that the roots can't be negative. They can't be 0 and they can't be negative. So that means that x has to be greater than 0 in order for it to be a root. So that's the only way you ever will be able to make f at x equal to 0. So we conclude here that a, b, and c, which are the roots, are positive. So the roots are positive. Okay. All right, so now where do we go from here? We have to now try to estimate what these roots are. What are their values? So one kind of way of doing it is sort of manually. Unfortunately, you're not allowed to use a calculator on this exam, so you got to crunch these numbers out sort of manually. But hopefully we won't have to do too many. Let's just do, I don't know, a few. Let's go up to like, let's go up to 6, I think. That should be good enough. We do know that the roots have to be positive, so we kind of understand that the roots will which side of the graph. I'm going to draw a little graph later, but at least we know that the roots will be on the positive side of the graph. When you plug these numbers in, you'll get the following. F at 0 will give you negative 1. F at 1 will give you negative 1. This will be negative 7, negative 13, negative 13, negative 1, and then 29. So if I were to draw a very, very basic graph and plug these roots, this is x, and this is f at x. So we've got negative 1, negative 1, down, this is for 1. For 2, it drops down to minus 7, so approximately here. And then for 3, it drops down to minus 13. For 4, it stays at minus 13, and then it comes back up to minus 1. And then it jumps up all the way up to minus 29 for 6. So I have no idea what this graph looks like, but my gut instinct is something like this. Trying to connect the roots here. Something like that. So obviously, there's a root right here, as you can see. And that was between 5 and 6. So that's a very, very approximate way of figuring out at least a ballpark estimate. So we can conclude that one root is between 5 and 6. So whatever it is, let's just say C. The roots are A, B, and C, right? Okay. And we are told that A is less than B is less than C, correct? If I remember correctly, yeah. And then if you remember from the previous part, using Vietas, you might remember that I had concluded that the sum of the roots was equal to 6, right? You can go back and check. So if one root is between 5 and 6, that means the other roots, A plus B, are less than 1 or greater than 0, right? For example, let's say C was 5.5, right? Then that means A plus B has got to be 0.5. So that's why we got this inequality here. So A and B are fractions, let's say. And B is greater than A, so I can conclude that both of these, since they're positive, both of these have to be less than 1. So A and B are less than 1. So we're getting there. Okay, let's keep moving forward here. Okay. Now the next step, I think, is to kind of figure out a little bit more information using another Vieta's formula, and that was the one that we got for the product of the roots, and that was that the product is 1 in part A of this question. So A, B, and C, if you multiply them together, is 1. Now, that means that A times B is equal to 1 over C, correct? And then from this, we concluded that 5 was less than C is less than 6. So that means if you take 1 over C, if you're just looking at that, then it would be between 1 over 5 and 1 over 6 if you just sort of do a reciprocal. And 1 over C is equal to AB. So A times B we can conclude is between 1 over 5 and 1 over 6. Okie dokie. So far, no tricks here. Keep going. Now, if we take this part, that AB is greater than 1 over 6, and also take into consideration that B and A, both of them, are less than 1, then that means that A must also be greater than 1 over 6, because if you're multiplying it by B and B is less than 1, then that means that this, when you take A and multiply it by B, you're going to get a smaller value. Like, for example, let's say you have that A times B is 0.3, let's say. And let's say you start off with A being 0.6, right? Well, when you multiply it by B, it's got to come down to 0.3, and that happens because B is less than 1. So let's say B is, for that to happen, would have to be 0.5. See? Because both of these numbers are less than 1. So if AB is greater than 1 over 6, then that must mean that A is also greater than 1 over 6, because A has to be greater than A times B. So that's the logic that we have applied to come up with this. So we can conclude by the same logic, right, if we just reverse the scenario, that B is also greater than 1 over 6. And then finally, we know that A plus B is less than 1, right? We had that some. Oh, it's right here. Yeah. So if A is greater than 1 over 6, which is the conclusion up here, and B is greater than 1 over 6, which is the conclusion here, then that means that A and B must be less than 5 over 6. So, for example, let's say A was 0.2. Then B plus A, since they're less than 1, B, the maximum it can be is 0.8. So if it's 0.2, the maximum it can be is 0.8. It would actually have to be less than that because it's less than. So that's why we got this upper boundary of 5 over 6. It's basically 1 minus the lower boundary because of that inequality. So there you go. We have, in a pretty decent way, approximated this. And I'm just going to put the fractional value, just 1.67 and 0.83. So we have gotten an approximation as to what A and B are. They're in between this range. So that's step 1. And then now step 2 of the 3 steps is we have to show that anytime you have A to the power of n plus B to the power of n plus C to the power of n, it will equal an integer for every positive value of n. Now, if you look back at 4a of this question, part A of this question, we already showed that with Vieta's formula that a to the power of 1, b to the power of 1 plus c to the power of 1 is 6. Then we also showed that a squared plus b squared plus c squared is equal to 26. We showed that a to the power of 3, b to the power of 3, c to the power of 3 is 129. A to the power of 4, b to the power of 4, c to the power of 4 is 650. And then finally, our final answer to the question was that a to the power of 5 plus b to the power of 5 plus c to the power of 5 is 3281. So as you can clearly see, if you extrapolate this, you will hopefully conclude that with the same process that was implemented in part A, we can show that all forms of a to the power of n plus b to the power of n plus c to the power of n will be some positive integer. And you can refer to your solution in part A to add to this step 2 of part B. And then now we come to our final part, which is going to put this all together. Now recall, we're trying to show that if c to the power of 2004 is calculated, and you have c to the power of 2003, that this is closer to its closest integer than this is. So for example, if this was 7.2 and this is say 6.3, 7.2 is 0.2 away from its closest integer. 6.3 is 0.3 away from its closest integer. So c to the power of 2004 is closer to its closest integer than c to the power of 2003 is to its closest integer. Okay, so how do we do that? Well, we're going to take some of the findings that we already have from our previous parts, that we found that a and b are both less than 1 and greater than 0. That was somewhere up here. It's one of the many. Here's this. Oh, here it is, right here. Okay, so that's something we definitely need. The next part we can conclude is that since a is less than 1, a to the power of 2003 will be greater than a to the power of 2004. See, normally if a number is greater than 1, let's say it's 2, then obviously 2 to the power of 2004 will be greater than 2 to the power of 2003. Correct? But since a is less than 1, this holds true, because if you keep multiplying it, the numbers keep getting smaller. So that's why a to the power of 2003 is greater than a to the power of 2004. And similarly, since b is also less than 1, b to the power of 2003 is also greater than b to the power of 2004. Okay, so now we add these, and when you add them, you get a to the power of 2003 plus b to the power of 2003 is greater than a to the power of 2004 plus b to the power of 2004. Okay? Now, recall we had estimated that a and b were in that range. So we will write that down here, that a and b are between 5 over 6 and 1 over 6. So this was approximately 1.67, and this is approximately 0.83. Okay. So on the side here, we'll do something. We know that a is greater than 1.67 and it's less than 0.83. Okay? So we're pretty comfortable about that. So if a is less than 5 over 6, so remember, we're trying to get some sort of an approximation. We're trying to get some sort of conclusion. So we can use a number like 0.9. It will make the math easy. And then start squaring. A squared would be less than 0.81. Let's square again. That will be a to the power of 4. That will be 0.7. Let's square again. A to the power of 8, about 0.5. Square again. A to the power of 16, about 0.25. And you do the same thing with b. It'll be pretty much identical since we're using the same range for b. B would be, let's just use 0.9 again. B squared less than 0.81. B to the power of 4 less than 0.7. B to the power of 5. B to the power of 8, I should say, when you square it. 0.5. And b to the power of 16, 0.25. And these are all approximations. So if you add this, a to the power of 16 plus b to the power of 16 is less than 0.5 if you add this and this. Okay, now we want to combine this guy and this guy. Well, according to this logic, if you have a to the power of 2004 here plus b to the power of 2004, and that's greater, it's less than actually a to the power of 2003 plus b to the power of 2003. That's just our finding from up here. And then if we combine that with this guy, keeping in mind that both a and b are less than 1, we can conclude that this is therefore going to be less than a to the power of 16 plus b to the power of 16, which is less than 0.5. So I just combined those two like that. Now we have to do a comparison. So compare at this point two possible integers. If you have a to the power of 2003 plus b to the power of 2003 plus c to the power of 2003, we have proven or concluded that any number of this form is going to be an integer. So I'll just call it m. And then similarly, if I have a to the power of 2004 plus b to the power of 2004 plus c to the power of 2004, that's also going to be an integer, and we'll call that n. All right. Now, from the first one, let's isolate for c to the power of 2003. This is going to be m minus a to the power of 2003 plus b to the power of 2003. And then this is c to the power of 2004, which is n minus a to the power of 2004 plus b to the power of 2004, like that. Correct? Okay, so far so good. Now, we've got m and n, and we have to talk about what we have to conclude. This part here, right here, is, we can conclude from this big long inequality that is less than 0.5. Okay? And also, this is also less than 0.5 from the same inequality. So what does that do for us? It shows us that m and c to the power of 2003 are very close. Because m is an integer, and this part you have to subtract, and it's less than 0.5, they're very close to each other, maybe 0.4, maybe 0.3. So we can conclude that c to the power of 2003, its closest integer is m. Okay, so for example, if c to the power of 2003 was whatever, 7.4, and this guy up here was 0.4, then m is 7. See, that's basically all that's saying. So hopefully that's not too abstract. And then in the very same way, and same logic, I guess, you can show here that c to the power of 2004, its closest integer is n. Because let's say c to the power of 2004 was 6.3, and this calculated to 0.3. Then n is 6. And we have already shown that n and m are both integers. So that's basically that story there. Okay, we are pretty much done. Because going right back to the inequality up here, but since a to the power of 2004 plus b to the power of 2004 is less than a to the power of 2003 plus b to the power of 2003, we conclude, therefore, that c to the power of 2004 is closer to its nearest integer, which is n, then c to the power of 2003 is to its nearest integer, m. So let's see why that's true. Let's say this here is, say, 0.3. This whole thing. Well, it's less than this, right, according to this inequality. So a to the power of 2003 plus b to the power of 2003, let's say it's 0.4. Well, putting those back in here, this in here, let's say it's 0.3, and then therefore this in here has got to be something a little bit bigger, 0.4. So that means that exactly what I wrote here, that c to the power of 2004 is closer to its nearest integer, in this case only 0.3 away, than c to the power of 2004 is to its nearest integer, in this case about 0.4 away. And that pretty much concludes this very challenging question.